stressed. That's, they went to Chicago, they didn't have as much time as usual to do these problems.
Hello everybody, welcome back to Calculus 1, brought to you live from Grand Rapids Community College, probably one of your favorite times of the week, and finally it arrived. And we have some good things planned for you today, but mainly this is in case you want to look back at anything, you'll check, and right away at the beginning of class it says, oh, today we checked homework from sections 2.2 and 2.3. Then we went on to discuss section 2.6, limits at infinity. And you say, I think we did that already. No, we did limits where the result was infinity or minus infinity. Now we're doing limits as you head for infinity. And the result might still be infinity, but not necessarily. Okay, then we're going to head to section 2.5, which is continuity of functions. And of course, I had to remind you that test 1 is planned for Thursday, September 19. And just a reminder that it covers the sections we've done through 2.6. So anything we do today in 2.5 won't be on the test. And any assignment connected with 2.5 won't be due till next Monday. And the review is available on Blackboard. It's been there for a while. Have you found it? Just wanted to remind you, it's a recommended test review. It's nothing I check. It's just something for you to look at so you have an idea what problems are like on the test. And I assume everybody can download it off from Blackboard. I mean, if you really put your mind to it. You'll also find solutions. That's more than answers. That's every single problem in the review worked out in detail, so that you don't have to be left hanging. But please don't look at the solutions till you've given it a good try on your own. Then compare to what you did. Otherwise, they won't help that much. Okay, just in case you haven't had a chance to look at the evens, I almost forgot to do 50 until somebody here said, last I checked, 50 was an even number. And I said, you're right, it's divisible by 2. Well, how come it's not up here? Because I went right past it. Sorry, but there it is now. And I was so nervous after that, I goofed right here. It goes down to minus 2, that second piece, third piece actually. So we'll leave that up just a little bit longer for those who maybe haven't been here that long yet. And then we'll see if we have to answer any questions from 2.2. And while you're maybe checking that, the format for Thursday is, when you first arrive, we'll do 2 things. We'll look at 2.6. Any questions, field those, because that is covered on the test. So anything in 2.6, of course, we'll do right away. And then we'll go to the test review and see if there's something there where you want more detail than what you saw. And then after that, if we're not quite done with continuity section 2.5, we'll quick finish it. If we are done with 2.5 already today, then after that we take the test. What do you do after the test is done? Leave. So that way, if somebody works a little more slowly, you don't have to worry about me coming around saying, I gotta have that test, because we have to move on. So after the test, that'll be the end of the class period for you. So if you want to get done early on Thursday, just fly through that test as fast as you can, and then you're out of here. But on the other hand, you're here anyway, so you might as well get them right. Does anybody need more time to check even answers? Okay, we'll give you a little more time. That means I have to do something to fill in the gap. Let me see. How about a math joke? Here it is. Are you ready? Did you know that the value of pi in Alaska is 3? That's what they use in Alaska. The approximation for pi is 3. Do you know why? Because it's very cold in Alaska. And you know that things shrink when it's cold. So 3.1415 shrunk down to 3. What do they call this version of pi that equals 3 approximately? They call it Eskimo pi. Now, aren't you glad you came? Now are you finished? You say, I was so intrigued with that joke, I stopped looking at the evens. I know that's the problem. They're kind of quiet on the main campus today, aren't they? They figure this is serious business. This is no laughing matter.
Well, I did hear what you said about pi in Alaska, and I do understand that.
You didn't follow that?
Yes, I followed it, but I have one question to challenge that. If things are smaller in Alaska, then wouldn't the radiuses be smaller too?
Radius of what? The igloo?
Yes.
Possibly. I have a feeling they use the building plan for the igloo, and after it's all together, they have to do it when you can pack the snow, so they have to do it when it's a little warmer, and then when it gets colder, I have a feeling it shrinks down a little. So that's probably true. Okay, are we finished with the evens? Okay, are there any questions about 2.2 first?
I have a question.
Yes.
Number 1.
On number 1?
Mm-hmm.
Okay. Is there something specific about number 1, or just?
I just didn't get it. Like, I don't understand why it's yes.
Okay, the explanation for number 1. First of all, this is the question. The limit of some function f of x as x approaches 2 is equal to 5. I could make up lots of functions where that's true, right? All right, they're saying, could this still be true and f of 2 ends up being 3? I remind you, a limit is telling you what? Where the graph wants to go. It's a predictor of where it's headed. Is it necessarily the answer to where it ends up? No. So, I could make up a function, for example, that's piecewise, because they're quite popular to show this sort of thing. And I can just say x plus 3 if x is not 2. And I can say the answer is 3 if x equals 2. That piecewise function. Now, if I were to graph that, what I get is a line with slope 1 and y-intercept 3. So it goes like this, right? But when I get to 2, I can't use this, so there'd be an open dot right above 2. And then it says when x is 2, the function is actually 3. So you have this line with an open dot on it right above 2, and then at 2 it's equal to 3. But really, basically, the explanation is this. Yes, this could happen, because the graph could have a destination of 5 from both sides. But when you actually get to 2, it doesn't end up there. It falls down to 3. Does that make sense?
Yeah.
So they're trying to get at the fact that a limit is not necessarily where the graph ends up. It's where it's headed. It's its destination. Now, do you agree that if I come in towards 2, I'm following this branch of the curve on the left side and it's headed for 5? And from the right, I'm following this branch. It's also headed for 5. But if there's a hole right there, it never really reaches 5. And it could actually end up at 3. This would be an example of a function where that happens. But that's it for number 1. I mean, that's all they're really after. A limit does not have to equal the value of the function there. It has to just be where the graph is headed. Okay, anything else from 2.2? Anything else that's not clear?
Number 9.
Number 9? Okay. On number 9, they have a picture of a function and they're asking questions. So what I'm going to do is bring that into view so that I can point. So zooming in on number 9, that's what the graph looks like. Okay, in particular, which one didn't you like the answer to?
Any of them?
Which one?
Any of them, I guess.
Oh, all of them?
Yeah.
Okay. They're asking for limits, right? So A, the limit as x approaches -7. I go to the graph and I ask myself, where is the graph headed as x moves towards -7? Well, -7's right here, isn't it? Okay, if I come in from the right, I'm following this branch. Where is it headed? Looks like it's going down, down, down towards -infinity. Okay, if you come into -7 from the left, you're following this branch. And where is it going? The same place. So we say the limit is -infinity. You say, that's not a number. No, but it's a destination. And that's what the limit is telling you. Sometimes it's a number, sometimes it's just infinity. Going up, 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 or down, 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 -infinity. Now, when I do x approaches -3, it's the same sort of deal. When I come in from the left, it's headed up towards infinity. When I come in towards -3 from the right, I'm following this branch, it's headed for infinity as well.
And think I had the
So
wrong.
since it's headed for the same place on both sides, the answer is infinity.
I think I had the wrong section on that. Never mind.
So you say my number 9 is fine,
Yeah, I
but you really wanted number 9 from 2.3?
I don't know. Apparently I didn't understand it when I looked at it, but now it makes complete sense, so I don't know what I was thinking.
Okay, do you see, just checking you out here, what's the limit as x approaches 6? Since it's up here.
From the left, it would be negative infinity.
Now, what's the limit as x approaches 6, period?
There, it does not exist.
It wouldn't exist because it.
Thank you. You're right, and you were explaining it because from the left it goes to,
Negative.
Negative infinity.
and from the right,
Infinity.
and if they're not the same destination, then we say the limit there does not exist.
Yeah.
Okay, you're good. Any other questions from 2.2?
I just have a clarification question.
Go ahead.
On 17, for the graph.
Yep.
On 17,
Yep.
for the graph, does it have
Yes.
to look exactly like what was in the back of the book, or as long as you have the same points, it's fine?
No, there's more than one answer possible.
Okay, that's what I thought.
All you have to make sure is that the conditions written down are met by your graph.
Okay.
But there's not one answer to something like that. Anything else? 2.2. Okay, so finding limits from a graph or numerically, okay, right? You think you might have to do that on the test? Probably. Do people usually do really well in that section? Yeah. They either get them all right or get them all wrong, it seems. But most of them usually get them all right, because if you understand the concept of a limit, you're good. From a graph, all you have to do is look. Numerically, just set up your table and fill it in and see where it's headed. Okay, then we'll go to 2.3, where you had to do limits not with a calculator or numerically, but using algebra. And how did those go? Did they manage to stump you at all? Or are they okay? 2.3.
Number
19? Okay. Okay, number 19 from 2.3. It says, please find the limit as x approaches minus 2 of x plus 2 over x to the third plus 8. Okay, is this one of those nice ones where I can do direct substitution? No, why not? Yeah, you end up with 0 over 0 actually, and you know what 0 over 0 is called in math? Is it called undefined? Not really, it's called an indeterminate form. You'll see this more later when we do something called L'Hopital's rule. But in one problem, 0 over 0 is going to be 3. In another problem, 0 over 0 is going to be minus the square root of 17. And sometimes people say, whoa, yeah, indeterminate form. We're not sure what it is. But it could be something. You see, if you plug in minus 2, you get 0 over 0. So what has to happen is the x plus 2 has to go if we're going to have any hope on this problem. Well, what's typically the way to get rid of the x plus 2? Factor. And I was kind of checking to see if you remembered how to factor a cubic. Okay, here's the pattern that maybe your pre-calc teacher skipped because they wanted good ratings, and students don't like to factor cubes. But see, I'm too old to care about ratings, so I do everything. Does anybody remember the pattern? Right, you start with a plus b, and then you have to just kind of plan ahead. What's the only way to get an a cubed if you have an a? So you need an a squared here, and you need a b squared there. Now the question is, what's in the middle? Well, something has to be in the middle, so all the middle terms cancel, right? Who recalls what that is?
Minus AB.
Yep. Somebody had a pre-calc teacher that didn't skip that topic, right? That's good. So there's the pattern to remind you of the sum of two cubes. You can also factor the difference of two cubes if that comes up. It's very similar. You can see just a slight variation in signs. Okay, now that you see the basic patterns, how would I factor x cubed plus 8? Well, think of 8 as 2 cubed, and then x is the a, and 2 is the b. See, x cubed plus 8 is like x cubed plus 2 cubed. And this matches that. So wherever you have an a, put a x. Wherever you have a b, put 2. So this would be x squared plus 2x plus 2 squared, 4. Okay, once you see that, what happens, of course? The x plus 2's cancel. And I get to take the limit as x approaches minus 2 of 1 over x squared plus 2x plus 4. Now I can use direct substitution. That'd be 1 over 4 minus 4 plus 4, if you substitute in minus 2, which is roughly 1/4. And I believe 1/4 would be close to the answer to 19. Could I have gotten that answer numerically? Probably, because 1/4 is 0.25. And if I pick my numbers very close to minus 2, I bet you eventually you'd see it narrowing down to 0.25. So, what is he saying? I don't know, on a test, if the teacher doesn't take the calculators away, and I end up getting an answer like 1/4, I might just say, I'm going to just quick check and see if the calculator numerically gets me there too. Even though this is what I would want to see. So it's like having a bob on your calculator. If the answer's halfway decent.
Wait, excuse me? Bob,
Yes.
the answer is 1/12. You wrote
It is?
1/4.
Oh, that's because I copied the wrong one. I used the second one and I was supposed to use this one, so this is a minus, which makes this plus, which makes it 1/12. Thanks for pointing out the reason I said you could check this numerically on your calculator. And you would have found the calculator's headed for 1/12. So you go back and check your work. Yeah, the factoring has a minus in the middle, which makes it 1/12. Okay. I was almost worried I'd have to point that out myself, but thank you for saying the answer is 1/12. Did I answer your question? Okay. Anybody else have something from 2.3? Which one? 23? Okay. What's the algebra for 23 that takes you to the correct answer? Okay, the original problem is a limit as x approaches minus 4 and it's 1/4 plus 1 over x over 4 plus x. And again, you can see that direct substitution isn't going to happen. You get another indeterminate form. Okay, when you have something like this, the key is get rid of the secondary fractions on top. Do you remember the advice we gave you for getting rid of the 1/4 and the 1 over x?
Common denominator.
What's the common denominator for those two little fractions on top?
4x.
So you multiply by 4x over 4x. Does that look familiar? Okay, in the denominator, we leave it in factored form. Why? Because I can't get an answer as long as 4 plus x is here. The only hope for this is that the 4 plus x might cancel. And not only is that probably the only hope for this, I'll bet you they do it that way at Kelvin too. It's not just hope. Okay, what happens when you distribute? What's 1/4 times 4x? Scratch paper. What is that? X. What's 1 over x times 4x? Is that good news? Very good news. So I end up just having to do the limit as x approaches -4 of 1 over 4x. Direct substitution will finish it now. It's roughly -1/16. And this time I hope that's even what Bob got. Okay, were there any others you weren't quite sure how to attack?
43.
Okay, 43. Okay, this is the limit as x approaches 0.5 from the left. And it's 2x minus 1 over absolute value of 2x cubed minus x squared. Ooh, absolute value. Okay, again, direct substitution leads me to 0 over 0. But we warned you about absolute value. Do you remember that absolute value of x is sometimes x and sometimes opposite x? Do you remember ever seeing that? When did you last see it? Last Thursday. Yeah, it's this one if x is greater than or equal to 0, and it's this one if x is less than 0, right? Okay, I've got to deal with the absolute value of 2x cubed minus x squared, right? Well, sometimes it's just going to be what's inside, 2x cubed minus x squared, right? And the rest of the time it's going to be the opposite of that. Okay? That's just being consistent. Absolute value of something is sometimes itself, sometimes it's opposite. Now I need the conditions under which that happens. Well, it's the first one if 2x cubed minus x squared is greater than 0, which means x squared times 2x minus 1 would have to be greater than 0, right? If I factor out an x squared. Now I'm multiplying two things and it has to be positive. When do you multiply two quantities and get a positive answer? If they're both positive or both negative, right? But what about x squared? He's always positive or at least greater than or equal to 0. So if this is always greater than or equal to 0, then this factor has to be positive also, or there's no hope? So the next step here is 2x minus 1 also has to be greater than 0. Actually, I can drag the equals with it, which means 2x has to be greater than or equal to 1, which means x has to be greater than or equal to 1/2, right? So the condition behind this one is x greater than or equal to 1/2. Well, what would be the condition for that one then? If x greater than or equal to 1/2 gives you this one, then the opposite would be when x is probably less than 1/2. You okay with that? I mean, we could work it out, but that's your only choice. If it's the positive version when you're greater than or equal to 1/2, then it's the opposite when x is the other, which is less than 1/2. Okay, now I have to know which of these two do I use. Well, look at your limit right here. Which side am I approaching 0.5 or 1/2 from? Which one of these conditions is left of 1/2? The second one. Okay, so the very next move for this one is, this is equal to the limit as x approaches 0.5 from the left of 2x minus 1 over the opposite of 2x cubed minus x squared. Are you okay with that? You see, the absolute value is either one of these two. I have to decide which one do I choose. Well, it all depends whether you're bigger than 1/2 or smaller than 1/2. Okay, if I continue this limit, I should be able to get an answer now. Because I can go minus, take out an x squared just like I did before, and I have 2x minus 1 left, right? And what happens to the 2x minus 1? And so I just have to take the limit as x approaches 0.5 from the left of 1 over minus x squared, which is minus 1 over 1/2 or 0.5 squared, which would end up being what? Negative 1 over 1/4, which is -4. So I think the answer to 43 is -4. Are you okay with that kind? How to handle absolute value?
Yeah.
Again, I get nervous because did your pre-calculus teachers skip absolute value in your class? Did they ever do this for you? Did you ever have to work with it? See, and you really like them because they made math easy. And now it comes back to haunt you. So you're not going to like me, but I'll guarantee one thing. When you go on to Calc 2, I didn't skip anything in Calc 1. Fair enough? So when they say, did you ever do this? You say, I don't remember doing it, but I'm sure we did. You say, but we'll give you bad ratings. And I say, that's fine. They can't fire me anyway. Why not? Because I already quit. And you can't fire somebody that quit. But seriously, absolute value, you got to be able to handle that. There's so many situations in applications where negative answers just are not acceptable. And the standard mathematical way of keeping things non-negative is put it in absolute value. It happens all the time. So I want to make sure you can handle absolute value, and limits is a great way to really dig and understand how absolute value works. But it's not complicated. All you have to remember is this right here. Absolute value of x is sometimes itself, sometimes its opposite. Okay, I don't have absolute value of x. That's okay. It's sometimes itself, sometimes it's the opposite of itself. And when you're doing a limit, you look at which side you're coming from and decide. Now, what would happen if they had a plus here? Then instead of opposite, you would put plain 2x cubed minus x squared. And I bet the answer would come out 4. But I'm nervous. Can you see that? This one comes out 4, right? The other one came out minus 4. So if that happened on a test, what would be the limit as x approaches 0.5 period of that function? I think you guys are going to be okay. You get it. Right? So why do we always check the limit from both sides if you're just coming into a number period? Because if the left and right hand limits don't match, you have no answer. Okay, is there anything else from 2.3?
10.
Number
10.
10, okay. A little more detail on 10. I tried to get this across on Thursday a bit. Let's try it again. In the A part, I have the rational expression x squared plus x minus 6 over x minus 2. They're wondering if that equals x plus 3. And you say, well, of course it does, because this is x minus 2, x plus 3 over x minus 2. And in algebra class, we applied the law of slashes, and we said the answer was x plus 3. So yeah, that's true. Except in algebra class, the fine print said you can only cancel what? If x minus 2 is not 0. And then you totally forgot the fine print because the instructions always said assume all factors are not 0. So you just focused on slashing, right? All right. Now we can't hang that loose anymore. The first question is, what makes two expressions exactly equal? Well, they have to have the exact same graph, for one thing. Another way to put it is, they have to have the exact same domain, the same range, and for every input, the output has to be the same. Right? Okay. If this is the first function, we'll call that one f of x, and this is the second function g of x, what is f of 1, for example? Four.
Yep.
And what is g of 1?
Also 4.
So they have potential, right, to be the same function? But it has to be true for every value. So I say, what's f of 2? Undefined, because it's division by 0. What's f of g of 2?
5.
Are these the same number?
Nope.
So are these functions exactly equal?
Nope.
And my explanation, because I had limited space to write it, was one way to say they're not equal is the domain of g of x is all real numbers. You can put any real number in and always get an output. And the domain of f is all real numbers except 2. So they can't be exactly equal because they're Domains are equal. All right, but then they want to see if you're really thinking, and they say, why can I do this? Because we do it. We take the limit of that function and we say that's equal to the limit as x approaches 2 of just plain x plus 3, right? So they say, aren't you being really inconsistent? You're saying these two functions are not the same, but yet you say their limits are the same. Well, what does the limit predict again? The graph's destination. Are both these graphs headed for 5?
Yes.
Yeah, their destinations are 5. Well, then what's the difference? This one actually reaches it, and this one never does. So the explanation for B is, if I take a limit as x approaches 2, x really doesn't equal 2, you're just approaching it. And as long as x does not equal 2, the limits will be the same. Because you can cancel the x minus 2 if you're approaching 2, because then you're not dividing by 0. Okay? Well, what's the difference if you graph it? Well, the calculator may or may not show it to you. Usually you have to know ahead of time. You see, one of them is this one, and the other one is that one with a hole right above 2. So one has a hole in it, the other one doesn't. Well, somebody in my other class said, look at my calculator. I graphed both of those and they look identical. That's why we don't use calculators as verification. I say, here, let me play with your window. And then all of a sudden the hole appeared. So why didn't the calculator show it in the first place? We have to understand how it graphs. It plots points and then connects the dots. That's all it does. Well, if it plotted a point here and plotted a point there and connected the dots, what would happen? Never find the hole. So how can you make the calculator show the hole in the graph? Make sure one of the points it picks is 2. One of the inputs is 2. Then it'll show the hole. But if it doesn't pick 2, it just picks one on either side and connects across, and you never know. But all that stuff you studied in pre-calc, so you understand that perfectly, right? Holes in graphs and how calculator can mislead and all that fun stuff. I don't know, does that help at all?
Yes, it helps greatly.
You're okay? All right. I hate it when I explain something and the student says, now it's worse than ever. I wish you just kept your mouth shut. It can happen.
It could, but it never happened to me.
I don't know. You just wait. Wait till the material starts getting hard. Any other questions from 2.3? 55?
57.
57. Okay. 57 is one of those to challenge you just a little bit. See if you can think a little bit in the abstract. Good for you, right? Stretches the mind a little. So if the assignment gives you a headache, you know it's a really good one. No pain, no gain. 57. And you say, he's stalling. He probably doesn't know how to do it himself. No, if I didn't know how to do it myself, I would write the problem very, very slowly and talk while I'm writing. In the meantime, hopefully I can see something to do. I forgot that was in the assignment. That's the phone in this room. I bet you some irate person doesn't like what I did and they're phoning in. Oh, we'll just let it ring. Pretend we didn't hear it. Of course, that could get irritating. We could pick it up and put it back down. You want to do that? Okay, the limit of f of x minus 8 over x minus 1 is 10. There's an unknown function f of x. But if you do this combo, they say the answer is known to be 10. They say, okay, now you tell me what the limit as x approaches 1 of just plain f of x is. What's that? Well, what do you do if you have no idea? You see, what did they say in that education class called 101? Oh, they said ask a student. You say, well, I don't want to steal your fun. Surely there's a bright student in here that has a good idea what to do. Students usually accept that and give you a pass. Anybody willing to help? They say, before you do that, though, you want to make sure you're getting along with the class, because if they think you're going to get stumped, they're going to relish watching you flounder.
Can you solve it for f of x?
Solve it for f of x. How can I do that? I thought about that, but I'm not sure how to solve for f of x, because technically there's parentheses there, and there's a limit on the outside. Excuse me. We have a phone in this room that insists on ringing. Grand Rapids Community College, a living classroom. You could, but this number won't do it because you ended up calling a calculus classroom. Sorry, so we can't really help you. Okay, bye. Watch, it'll ring again. I needed that though, because I needed more time to think. But as I was saying, this is all inside, right? And I like the idea, but I'm not sure how to get at the f of x.
You have to switch cameras.
So you're right, if I could just figure out what f of x is, then I could just take that limit and be done. But I have a feeling they constructed it so it's going to be hard to get at the f of x. In fact, I suspect we're going to have to find the answer without ever knowing what f of x really is. Is it possible, do you think, to find its limit even though you don't know what the function is? Well, yeah, it's just its destination. Any other ideas, either on how to get at the f of x or a different plan? Now, typically when we have a fraction, right, what do we want to happen? In other words, to do this limit by direct substitution presents a problem, right? Where's the problem? In the denominator. I end up with division by 0, right? Or I just do direct substitution, right? But how do we typically get rid of that expression in the denominator? Yeah, we try to get another factor on top so it'll cancel. Trouble is, if I don't know what f of x is, I don't know how to factor it. So how about this? The limit as x approaches 1 of f of x minus 8 over x minus 1. I think he's stalling. He just keeps copying the problem over. Times the limit as x approaches 1 of x minus 1 should equal 10 times the limit of x minus 1 as x approaches 1. What do you do to go from the first one to that one? I think you just multiply each side of this equation by the same thing. Is that a legal algebra move? If you have an equation, there's one, you can multiply each side by the same thing. I multiplied each side by the limit of x minus 1 as x approaches 1. You say, well, why did you do that? Because I have a property that says if you take a limit times a limit, you can write it as a single limit. Now, normally we do it the other direction, but what would it be the limit of if I wrote this as a single limit on the left? I mean, I think you agree the limit as x approaches a of f of x times the limit as x approaches a of g of x can be written as one limit. I'm sure that's a property. Is that true? All right, so applying that, wouldn't I get f of x minus 8 over x minus 1 times x minus 1? Yeah? All right, what happens on the other side? Well, isn't x minus 1 a polynomial? So how can I actually get that limit?
X substitution.
Which would give me 0. Okay so far? All right, now what can I do on the left? Get rid of that x minus 1 like I needed to. So now I have the limit as x approaches 1 of f of x minus 8 equals 0. Okay, I have another property that says if you have a limit of a difference, you can write it as what? You can separate it into the limit of f of x minus the limit of 8. And that still equals 0. But what's the limit of a constant like 8? No matter where you're going, whether you're headed for 13, 100, 56, minus 19, 1 even, the limit of 8 is 8. So I have the limit as x approaches 1 of f of x minus 8 equals 0. Add 8 to each side. And I think I've answered the question. What is the limit of f of x as x approaches 1? It's 8. Did I ever find what f of x was? Nope. But I found its limit. I'm not saying that's the only way to do it, but does it make sense? Now, if I were a student, I would have a question. It's right here, this step to that step. And I would say, there's a condition. It says you can only make one limit out of 2 if both individual limits exist. I would say, I can see why this one exists. We already know, this one's going to be 0. But how do you know that one exists? I mean, when you divide by x minus 1, maybe the answer is does not exist. And we slide this way, and what does step 1 say? The limit not only exists, but the answer is 10. So, in essence, step 1 says the limit exists. And if the limit exists, I have the right to make one limit out of 2, if each limit individually exists. But you have to watch those conditions before you just kind of glibly apply the limit laws. Okay?
So if it hadn't said it equal 10, you wouldn't have been able to do it or anything? Because you have to know that the limit exists.
Yeah. Well, I couldn't have done it this way. I would have had to find a different way. Yeah. Okay, so for what it's worth, hopefully that gives you an idea how you could get the answer one way on 57. Have you had enough time to view it? You say, ah, you worked it so slowly, I could have written it down 3 times. Sorry. Any other questions from 2.3?
6E.
Number
60.
18?
60.
60.
But I can do 18.
Good, but it would be a waste of time if no one needs help on it.
Okay. On 60, answers can vary. They just want you to find a couple of functions where the limit of the sum exists, but individually the limits don't exist. In other words, they're wondering, is it possible for the limit of f of x as x approaches some a does not exist, and the limit of g of x as x approaches the same a does not exist. And yet, if you were willing to take the limit as x approaches a of the sum of the two, you actually get something. And they say, can you find any functions? Well, being kind of in a hurry, I said, well, all right, if f of x is 1 over x, and g of x is minus 1 over x, well, how was I supposed to get those answers? You weren't. You're supposed to make up something, just like I did. There's probably all kinds of answers, okay? And if you let a equal 0, do you agree the limit of f of x as x approaches 0 does not exist? Now, if you're not sure about that, you graph 1 over x, which goes like this and like that. Okay, down here. Why does the limit as x approaches 0 does not exist? Because from the right you're headed for infinity, and from the left you're headed for, okay? Also, the limit as x approaches 0 of g of x, choosing this one, does not exist. Well, what's the graph of that one? I'll put it right up here. It's just this one and that one. So for g of x, which is minus 1 over x, from the left you're going to infinity, from the right you're going to minus infinity. All right, what happens if you add them first and then take the limit? Well, the limit of f of x plus g of x and that's as x approaches 0, would be the limit as x approaches 0 of 1 over x plus minus 1 over x. But what's 1 over x plus minus 1 over x? So this is really just doing the limit as x approaches 0 of 0, which is a constant. And the limit of a constant is always itself. So I came up with 2 very uninteresting, quite trivial functions, but hey, I answered the question. It was getting late and I didn't feel like being exotic. Okay? I'm sure there are more. That just kind of came to mind as a quick, easy solution. And I hope it makes sense what they were trying to illustrate. So the individual limits don't exist, but if you take the limit of the sum, you actually get something. Can happen is all they're pointing out. In other words, if they had a true-false question, if the limit of f of x does not exist and the limit of g of x does not exist, does that mean the limit of their sum does not exist? Not necessarily. Here's an example where it does. Okay, anything else from 2-3?
63.
63. Okay. Okay, on 63, they want you to take the limit as x approaches minus 2. And the numerator is 3x squared plus ax plus a plus 3 all over x squared plus x minus 2. Question. If you tried to take the limit just as it is, you end up with 0 in the denominator, don't you?
Yes.
They're saying if you pick just the right a, could you make this limit exist? Well, they're hoping you think back to some previous exercises. This is a rational function. And the reason we're having problems just the way it is simply that the denominator has factors of x plus 2 and x minus 1, right? That's why I'm having a problem. Okay, now think back. If this limit is to exist, what has to happen?
You need to get rid of the x plus 2.
The x plus 2 has to cancel with another factor like it on top. So now what does the problem boil down to? If I could just pick an a, so that x plus 2 is a factor of the numerator, then I'd get an answer, wouldn't I? So now what I'm going to try to do is find a so that x plus 2 is a factor of 3x squared plus ax plus a plus 3. That's what I'm going to do. Well, how can I find an a so that x plus 2 is a factor? Well, you have to go back into what's the meaning of a factor. Is 3 a factor of 12?
Yes.
Yep. How do you know?
Because 12 divided by 4 is 3.
I think you meant 12 divided by 3 is 4 with no remainder. Isn't that what you naturally think? So how do you answer the question, is something a factor, something else? Well, can you divide and not get a remainder? So is 3 a factor of 12? I don't know. 12 divided by 3 is 4. Remainder is, yeah, remainder is 0. Okay, I'm going to do the same thing here. X plus 2 is a factor of this if I can divide x plus 2 into it and get a remainder of, okay, so here goes. X plus 2 divided into 3x squared plus ax plus a plus 3. I'm going to actually divide and see what a has to be so the remainder comes out 0. Okay, how do you divide? We start by taking 3x squared and divide by x. We did this once before in chapter 1. What's 3x squared divided by x? Okay, 3x times x plus 2 is 3x squared plus 6x. Okay, now what do? You subtract. Okay, what's ax minus 6x? A minus 6 times x. You okay with that? And then drop down the next term. Well, this term is the a plus 3. It's not just a, it's the term without any x in it. So you drop down the entire a plus 3. Sometimes that throws people off a little bit. Okay, now take a minus 6 times x and divide by x, and what do you get? right? A minus 6 times x divided by x is a minus 6. What's a minus 6 times x plus 2? Well, a minus 6 times x is a minus 6x. Plus, what's a minus 6 times 2? 2a minus 12. How are you doing so far?
Good.
Okay, now subtract. What happens when you take a minus 6 times x and subtract a minus 6 times x? 0. All right, now for the big test. What's a minus 3 subtract 2a minus 12? A minus 2a is?
Negative A.
3 subtract negative 12.
15.
Are you okay with that?
Yes.
So when I divided by x plus 2, the remainder was minus a plus 15, wasn't it? But if x plus 2 is to be a factor, this remainder has to be 0. Now can you see what a has to be? So the answer to part A is, if you let a equal 15, you're supposed to get an answer. And they say, okay, fine, now tell me what the answer is. Okay, well, we'll just put 15 in for A and C. So now it becomes the limit as x approaches minus 2 of 3x squared plus 15x plus 15 plus 3, and that's still over x plus 2 times x minus 1. Now, if I did the math right, x plus 2 should be a factor of the numerator. Let's see if it is. What I really have up there is 3x squared plus 15x plus 18, right? Okay, let us factor the top. First you take out a 3. Well, I like this problem. It really lasts. Get your money's worth out of this one. And now we factor some more. And guess what the factors on top are? I just dare bet you that one of them is x plus 2. I have a feeling. Is that true?
Yes.
Okay, then what's the other one?
X plus 3.
By Henry, look at that. If I did let a equal 15, I do get a factor of x plus 2, which cancels with the one on the bottom. And now I can finish it by substitution. If you put a minus 2 in for x, what happens on top? I think you get 3, right? What happens on the bottom? So the limit is actually you like that kind of problem? I love that kind of problem. I mean, I could do those for hours. Isn't that one reason why you like math so much? I mean, think about what's involved. You see, you think back on all the stuff you've learned. You start asking yourself questions. You know, it's okay to talk to yourself where you're doing math. If you're self-conscious about it, just go in your room and close the door. It's okay. That's what I used to do. And my mother used to say, "Who's in that room with you?" I said, "The guy helping me with my math." "Well, who's that?" I said, "Myself." So from then on, so she wouldn't ask me who I was talking to, I would say, "Self? What about this?" And then you get an answer. So I asked myself, what's it going to take for this limit to exist? Self. I thought about it. Oh, well, if you remember problems before, x plus 2 has to cancel as a common factor. Okay, self, what does it take for x plus 2 to be a factor of the numerator? Well, if you divide, the answer has to be, remainder rather, has to be 0, and on you go. See all the elements of this problem? And when you do a problem like that, it's really good for the mind. So you may not actually do problems identical to this, but the thought process is what they're after. Can you think that way? And supposedly, calculus can help you think logically and put a logical sequence together to come up with a solution. Good for you. So that's why even dentists take calculus. But it might be because that often ends up on the teeth, and if they've taken calculus, they might know better how to remove it. I don't know. Any other questions from 2.3? Have we covered what you need?
49.
49? Okay. That's another one of those infamous absolute value problems, isn't it? So I bet you have an idea ready of what we're going to be doing. Okay, g of x happens to be the function x squared plus x minus 6, and it's over absolute x minus 2, not just x minus 2. In part A, they want the limit of g of x first as x approaches 2 from the right. Then they want you to do the limit of g of x as x approaches 2 from the left. And after you check those two answers, then they're going to say, well, does the limit as x approaches 2, period, exist? Well, yes, if these two limits are equal. No, if they're different. Well, when there's absolute value, you know what I'm going to do. I've got to rewrite the problem without absolute value in it, or I just can't do it. So I say to myself, how do you handle absolute value? Absolute value is no big deal. Sometimes it's what's inside, and sometimes it's the opposite of what's inside the absolute value, right? When would this be true? If what's inside is greater than or equal to 0? When is this true? If what's inside is less than 0. Have we traveled that road before? Okay, let's refine it a little. In other words, it's x minus 2 if what? What's another way to write my condition?
X is greater than or equal to 2.
And it's the opposite of x plus 2, right? If I fix it, if what?
X is less than 2.
You with me? Now, as soon as you do that, you know you're on the right track, because I want to approach 2 from the right. Approaching 2 from the right is bigger than 2 or less than 2? It's bigger than 2. So if you are approaching 2 from the right, the limit of g of x as x approaches 2 from the right is going to be the limit as x approaches 2 from the right of x squared plus x minus 6 over what? Well, what is the absolute value of x minus 2 if you're to the right of 2? Just plain x minus 2. And now you got something you can do, see? Because that becomes the limit as x approaches 2 from the right of x minus 2, x plus 3, all over x minus 2. You know the routine. These cancel, and the answer comes out what? Now you can substitute. 5. So the answer to A, the first part, is 5. Okay? Now I want to do the same problem if you're approaching 2 from the left. Well, what does the problem become if you're approaching 2 from the left? It becomes x squared plus x minus 6 over what? Well, if you're approaching 2 from the left, you are less than 2, which means you use this version. Isn't that neat how that works? Come on, you got to be sort of into this, right? I mean, even if absolute value wasn't your favorite topic before, do you see why this definition is so critical? The one they might have skipped in pre-calc or maybe glossed over a little bit too much, I don't know. Well, I'm not quite out of the woods yet. This still factors into x plus, or rather x minus 2 and x plus 3. But I need to get rid of the x minus 2. How can I get an x minus 2 on the bottom?
Multiplied by negative what?
Factor out a negative 1 is what he really meant to say. And now they cancel. And what's the answer by direct substitution? All right, so the limit from the right is 5. The limit from the left is minus 5. So what's the limit period? Does not exist. And then they say, okay, look at the graph and you can see a picture of what you just discovered algebraically. You can graph that okay, or you want to see a graph? You're okay? Do you know where to find absolute value on your calculator? It's usually in the math menu, but yeah, it's just ABS. So you can get it right out of the catalog real quick too, because it's the very first one in there usually with ABS. So it's ABS and then parenthesis x minus 2. And you should see a graph where coming in from the left of 2, it's headed for minus 5, and coming in from the right, it's headed for 5. Okay, is there anything else in 2.3 that you're not quite sure of? 33C. Oh, you guys are really working me today. You say, you made the assignment, it's your own fault, right? Okay, 33. The C part. Okay, I kind of like 33 because they ask you to do the problem 3 ways. They say draw a graph and see if you can guess about what the answer is. Then they say make a numerical table and guess again. See if your answer is anywhere close. And then do it algebraically and see how your guesses were doing. Okay, we're going to do the algebraic method. It's the limit as x approaches 0 of x over the square root of 1 plus 3x, and then subtract 1 from that. The first thing you have to notice is that the 1 is not under the radical. Did you see that? Okay, the standard procedure we talked about on Thursday was multiply this by the conjugate of the radical over itself. The conjugate of the radical is the square root of 1 plus 3x plus 1. But to maintain equivalence, we must multiply the numerator by the same quantity. Does that look familiar? Okay. The numerator we do not multiply out. because we're hoping that the factor of x cancels. We do multiply out the denominator, but we're supposed to do it in our head because of that a minus b, a plus b pattern, which is the square of the first term. What's the square of the square root of 1 plus 3x?
1 plus 3x.
Minus the square of 1. And things are looking just wonderful because I have x times the quantity square root of 1 plus 3x plus 1 all over what?
3x.
And that's very good news because what may I do?
You can factor and cancel the x's.
But you're not supposed to divide if it's 0.
Yep, now you are.
It's not 0 because you are approaching it. You're not there, you're approaching it. Okay. All right, now I can finish it by substitution. If you put 0 in place of every x that remains, what happens on top? Well, you get 1 plus 0, square root of 1 is plus another 1. And the bottom you just have a 3. I think the answer is 2/3. So when you did, especially part B, I hope you're getting 0.6 repeating. So when you have a radical involved like this, what do you typically do? Multiply by the conjugate over itself. And we don't care if the radical's upstairs or downstairs, it's still the same technique. Anything else? Is there anything left?
50.
There is one left. 50. Okay, which part?
Any of them?
Okay, that would include A then, right?
Yep.
Okay, I want the limit of g of x as x approaches 1 from the left. Okay, here's g of x as a piecewise defined function. Sometimes it's x, sometimes it's 3, sometimes it's 2 minus x squared, and the rest of the time it's x minus 3. Conditions are very important though. It's only x if x is less than 1. It's only 3 if x is actually equal to 1. It's 2 minus x squared if 1 is less than x is less than or equal to 2. And finally, it's x minus 3 if x is greater than 2. Okay, I want to take the limit of this function as x approaches 1 from the left. What you have to do is decide what piece are you following if you're approaching 1 from the left. What's left of 1? Less than 1? Left are the numbers less than 1. What is the function when x is left of 1, less than 1? It's the first piece, isn't it? Okay, if I just take a function y equals x, because that's the one I have to use for part A, what kind of a function is that? Very simple polynomial function. And how may you get the answer to the limit if it's a polynomial? Direct substitution. Okay, just put 1 in there. And what do you get? If x is 1, y is
1.
That limit is 1. Yeah? Or is that too easy? It made you nervous. Okay, what's part B? Well, it says find the limit if you're approaching 1 period. Not from the right, not from the left, just approaching 1, period. That's the double I part. I think I'm seeing that correctly, 1, period, right? Okay. Well, we already know the answer to A is 1, right? Now I've got to check what's the answer if you approach 1 from the right. Well, what branch am I on if I'm approaching 1 from the right?
The third one.
One from the right.
Bigger than 1? Okay.
Wait, 1 plus, this is 1. This X approaching just 1.
I know, but to find what it's approaching when it's just approaching 1, I got to know what the left and the right are. Because if they don't match, the answer does not exist. Now the tendency is just to find g of 1, which is 3. No, when you approach 1, you're not at 1. So when you're approaching 1 from the right, you're greater than 1, so you're on this function right here. So this is really doing the limit as x approaches 1 from the right of 2 minus x squared. That's the function you're following when you're to the right of 1, bigger than 1. Well, what is that? Well, again, it's a polynomial, so you can just do it by substitution, and you get 1. Ah, so the limit from the right, the limit from the left is the same number, 1. Therefore, what's the answer to part 2? It's 1 because it's the same from the left and right. A little tricky on that one, but be careful, be on your toes, and always remember, what does the limit really mean? How far do you want me to go?
That's good.
G of 1 just means evaluate the function at 1. Well, when x is 1, it says g is 3. And that's why when you start graphing it, and you're getting close to 1 here, you see the first one is headed towards 1, but doesn't quite reach it. And then when you do the second piece bigger than 1, you're also headed for 1. But you're going down here, so it kind of curves down like that. So you're headed for 1, but when you actually get to 1, you're not at 1, you're way up here at 3. That's kind of the picture of what's going on initially. And that's why they said draw the picture when you're done, so you can actually see what the graph looks like to produce the results you got in part A. But he says he's okay now, so we'll stop. Anything else from 2-3? Okay, it's quiz time. Now, for those of you on the main campus, was there still an envelope on the table in the front?
Yeah.
Did anybody open it?
No.
Okay, in it you'll find quizzes and an attendance sheet. So make sure the attendance sheet goes around. And you can pull the quizzes out, and I will shortly tell you which numbers I want you to copy from your homework. But first I have to pass them out here. Now, to you people that are here, your attendance sheet is always in the middle drawer here. All you have to do is pull it out and grab it. Did anybody pull it out on Thursday? No, it was still there blank, which means all of you got an absence on Thursday. Pass 2 attendance sheets around. If you weren't here Thursday, make sure you sign out. If you're not here today, but you were here Thursday, make sure you sign the Thursday one. Okay. if you are ready, problem number 1 is section 2.2, page 97, problem 21. Number 2 is section 2.3, page 107, problem 15. Number 3, section 2.3, page 107, problem 21. And number 4 is section 2.3, page 107, problem 26. As soon as the quiz is done, we'll have our break, and then we'll move into 2.6. We spend a little more time on homework, which is fine if you have the questions, so we may not get into 2.5 much, but that's okay. We're still on target. And most of you are on target too, right? Or are you wandering around in Myers somewhere? It's important that you stay on target. If you do wander around in Myers, watch out who you get for a checkout.
Actually got a question. Can I get at least the equation for this one? Because I'm pretty sure I can solve it. I just didn't write down the equation.
Well, what do you have in your homework? Did you do that one?
I did, but I'm pretty sure I did it wrong, and I don't have the original equation to do it from.
See, technically, I just want to see what you did in your homework.
I know it's wrong from what we did earlier today. And
Anybody still working on their quiz? Anybody at the main building still copying? They all left. Wonder if they'll come back. Almost time to do 2.6. Okay, section 2.6 is cleaning up on the limits. As I mentioned before, 2.5 is a different topic called continuity. That's why I go to 2.6. We're on limits, let's finish them up before we go to a different topic. This will be as far as the test goes. It's not a real long section. In fact, we start out with our famous Toyota trick called recall. What would I like you to recall? Well, if I have a function f of x, which is a rational function, 8x squared plus 5, all over 3x squared plus 5x minus 2. Nice little rational function there. When we reviewed these functions in chapter 1, we said one of the characteristics you expect with a rational function is what? The occurrence of asymptotes. Remember? If I take f of x and factor the denominator, which would probably be 3x and x for sure, and it would probably be a plus 2 here and a minus 1 there, I would guess, right? Something like that. Then it probably hits you and you actually recall what causes vertical asymptotes. Denominator equal to 0. Remember? What makes the denominator 0?
If at least when f of factors equals 0.
So when x equals 1/3, or when x equals -2. So if I were to draw a picture of this, right here at 1/3, right about there, I'd expect to see a vertical asymptote. And then another one here at -2. Okay? But that's part of the recall. The other part of the recall is this has another kind of asymptote too. What kind? See, vertical asymptotes, x equals 1/3, x equals -2, okay? f of x also has what? Do you remember when we reviewed that? Yeah, a horizontal asymptote. Now, do you remember how you were taught to get it quickly from pre-calc? We even sort of reviewed that in chapter 1. I guess that was a waste. Remember how to get the horizontal asymptote? They taught you a nice little technique in pre-calc. And when somebody said, how do you know that works? They said, go to calculus and they'll explain exactly why it works that way. And see, that's what this section does, for one thing. But first you have to recall what the horizontal asymptote was. It's y equals something, you know, horizontal line. Anybody remember what it is for that example?
In a case like this, I think, is it 8/3?
Yes, it is. Y equals 8/3. And you say, oh, yeah, that's right. You take the leading coefficients of the common highest power on top and bottom. You were taught that in pre-calc. So there's an x squared on top, there's an x squared on the bottom, and the horizontal asymptote would be y equals the ratio of the leading coefficients. Well, what if the highest power on top was x to the first and you had an x squared on the bottom? Well, then you write the top as 0x squared plus x and then plus something. And then the ratio of 0 to whatever the bottom is would be 0, so it's the x-axis, you know, y equals 0. Well, what if you have a power of 2 on top and just a power of 1 on the bottom? Well, then the ratio of the leading coefficients would be something divided by 0, which means no horizontal asymptote doesn't exist. Do you remember those days? Okay, so if I went to 8/3 here, which is about 2 2/3, right? There would be a horizontal asymptote through here. In fact, the graph actually does this. If you want to check it, and then it does that. And then on this side, it comes down and then comes back. Okay, one thing you notice right away is this. Can a graph ever cross a vertical asymptote? Not a vertical, because it's undefined there. Can it ever cross the horizontal asymptote? Yeah, in fact, this one does on this side. It goes, crosses it, and then comes back and gets close. It's not unusual. So you can intersect a horizontal, but you can never intersect a vertical because the graph is undefined there. Okay, the other thing I want you to recall is how calculus describes the vertical asymptote. So that's the calculus description of a vertical asymptote. Okay? Now, where are mine? Well, there's one at -2 and there's one at 1/3, right? Okay, when you approach a vertical asymptote, what choices does the curve have? It can't cross it, so it either veers up to infinity or veers down to -infinity. So calculus describes it using limits. So for this particular case, we say the limit of this function f of x as x approaches -2 from the left is what? I mean, assuming I drew it correctly. If you approach -2 from the left, where is the graph headed?
Infinity.
Likewise, if I say limit of f of x as x approaches -2 from the right, you would say?
Negative infinity.
If I just said, what's the limit as you approach -2 period, you'd say, does not exist. And you could do the same for 1/3. The point is, you can describe vertical asymptotes in terms of limits whose answer is either infinity or minus infinity. Okay? Now the question is, how could we describe the horizontal asymptote? So next is calculus description of a horizontal asymptote. Okay, we'll bring the graph back in sight. What was the horizontal asymptote again?
8/3.
Y equals 8/3, because you want it to be horizontal, right? Okay, when does the graph get close to 8/3? Very nature of a horizontal asymptote. It gets closer and closer to 8/3 if you go to the far right. Right? The further you go to the right, the closer it gets to 8/3. And in this case, it also gets close as you go to the far left. The further you go to the left, the closer the curve gets to 8/3. So how can we describe a horizontal asymptote? We can use limits. The limit of f of x as x approaches infinity. Notice the contrast where the infinity is now? Before, for vertical, the answer is infinity or minus infinity. Now the x is approaching infinity. What does approach infinity mean? Go to the far right. Okay? And what's the answer? As the graph moves further and further to the right, where's it headed towards? It's getting closer and closer to what? 8/3, isn't it? That would be a way to describe the horizontal asymptote in this example. As x approaches infinity, the graph squeezing in closer and closer to 8/3, the horizontal asymptote. Now in this particular case, the same would be true here. Okay? Now, does it have to approach it on both ends? No, just one is enough. Can you think of a curve which only has a horizontal asymptote on one side? One that we studied? How about that one? Do you recall the graph goes like this? So, if I said, what is the limit of e to the x as x approaches minus infinity, what would the answer be if I drew the graph correctly?
This?
Well, as you go to the far left, that's minus infinity, you're getting closer and closer to 0. The limit is 0. What would be the answer if x approached infinity? Well, the further you go to the right, what does the graph do? Yeah, the limit of e to the x as x approaches infinity is infinity, because it just keeps increasing. Okay, can you get with that language how it describes asymptotes in terms of limits? So one more time, if you have a vertical asymptote and you describe it with a limit, the answer is either infinity or minus infinity. If you want to describe a horizontal asymptote, then x approaches either infinity or minus infinity, and the answer is some constant, whatever the horizontal asymptote is, wherever that level is. Okay, that's kind of the introduction. Okay, from here, we try to justify why what you were taught in pre-calc, namely when you have a function like this, you can just look at the ratio of the leading coefficients and the answer is the horizontal asymptote. Okay, we can justify that now using limits and calculus. So this is B using limit properties to find horizontal asymptotes. Number one is an important additional. That means we didn't do it in 2.3. We waited till we needed it. Important additional property of limits. Fortunately, it's a very logical one, and so it shouldn't be hard to understand. It says, if R is any positive rational number. What does that mean? What are the rational numbers?
The ones that involve division.
So rational numbers include all the fractions?
Yep, all fractions.
Anything else? Integers, because integers are fractions where the denominator is 1. Yeah, rational numbers are the integers plus the fractions. Okay? Now it says if R is any what kind? So that could be something like 3, 13, 1/2, 2/3, 56/7, numbers like that. Okay? And x to the r power is defined for all x, and k is any constant real number. Okay? So r is going to be the exponent on x. K is any constant you want to pick, 13 minus the square root of 32, whatever you want. Okay? Then, here's the conclusion. We'll see if it's logical. If you take the limit as x approaches either plus or minus infinity, we don't care whether it's plus or minus, of a constant k over x to the r, the answer is always something. Now let's think about that logically. This is a fraction, right? The top stays constant, never changes. What's happening to the bottom as x heads for either infinity or minus infinity? Well, as long as r is a positive real number, okay, then the denominator is doing what?
Going up?
Increasing. Getting bigger?
Yes.
Okay, if it's a positive rational number, then the denominator is growing. What happens to a fraction when the top never changes and the bottom gets bigger, 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 bigger?
Closer to 0.
It's getting smaller and smaller, isn't it? So every limit of this type has to have an answer of 0, right? Are you okay with that? I mean, a typical example would be 13 over x squared, right? You take a limit of that as x approaches, we'll say, infinity. Well, if you did a numerical and you did 2, you get 13/4, right? If you picked x equal to 10, you get 13/100. If you pick x equal to 100, then you get 13 over what? 10,000? 100 times 100. What's happening to that fraction? It's getting really small, right? And I only did x equal to 100 yet, and I'm headed for infinity. So any fraction of this type under those conditions has an answer of 0, new limit property. But that's only true if x is approaching infinity or minus infinity. It's not true if x approaches 2 or 3. And one little mistake that occurs on the test sometimes is people like this answer so much for a limit that they give an answer of 0 when x approaches 50 or x approaches 1. No, it's only if x approaches infinity or minus infinity. Okay, now we're going to take an example to kind of verify what you were hopefully taught in pre-calc. So that's the property. This is number 2, an application of it. Find the limit as x approaches infinity of 7x cubed plus 4x all over 2x cubed minus x squared plus 3. Okay? Now, without doing any work whatsoever, you should be able to tell me the answer. Because on a problem like this, when you take a limit as x approaches infinity, they're only asking the answer is what? The horizontal asymptote, which occurs where? That's the answer. Okay, that's pre-calc. Now, what's my job? To show you why pre-calc could teach you that. Tell you that works, okay? Well, it has to do with a little algebra in this property that we just did. Okay? So, starting from scratch, limit as x approaches infinity, 7x cubed plus 4x over 2x cubed minus x squared plus 3. Okay, when we approach this, what's the theory? The theory is this. I want to get this situation I'm boxing in as often as I can. Because every time I have this situation and the limit as x goes to infinity will be 0. So I look for the highest power of x, which is, and I multiply numerator and denominator by 1 over x cubed. Okay? Now distribute that. What's 1 over x cubed times 7x cubed? Don't hesitate,
7.
you scare me terribly, and I don't have that good a heart.
7.
You want me to collapse in front of you, do you? Well, maybe you do, don't answer that. Anyway, what's the answer? 7. Should be instant. You shouldn't even have to go over here and say, oh, let me see. Oh, I see. Oh, 7. Yeah, okay. They're going to laugh at you if you do that. Okay, what's this one? 4x times 1 over x cubed.
That would be 4 over x squared.
Thank you. Why are you hesitating? You really know that, don't you? I mean, you're not lost, are you?
Nope, I'm not.
I know, but how about the other people? Are you okay?
Yeah.
All right. Try it again. What's this one? 2x cubed times 1 over x cubed.
2.
2. All right. Things are looking up. Now 1 over x cubed, this times minus x squared.
Minus
Negative
1
1
over
x.
x.
Ah, okay. Now I feel a lot better. Finally, times 3. Now, by doing that, do you notice I've got a lot of situations where I have a constant over a power of x? Now, we're not going to, break it all down and drag this problem out, but technically, our limit properties say you can do the limit of the top and the limit of the bottom separately, remember? And then on top, you're going to have a limit of the sum. So I'm just going to jump here and say eventually, and when you do this problem, you probably won't even write this much. You're going to end up with a limit of 7 plus the limit as x approaches infinity of 4 over x squared over the limit as x approaches infinity of 2 minus the limit as x approaches infinity of 1 over x plus the limit as x approaches infinity of 3 over x cubed. Okay? So by applying different limit properties, I can get to that point very easily. Okay, at least the first time through I wanted to write that much so that it was perfectly clear how this turns out. What's the limit of a constant no matter where x is going?
The constant.
Itself. What's the limit of a constant over a power of x like this? 0. If x goes to infinity or minus infinity. Bottom. 2 minus 0 plus
0.
for an answer of, now do you see why they could say, just take the ratio of the leading coefficients? That's the basis for what they said. And they weren't pulling your leg for once when they say, when you take Calc 1, you'll get this question answered. Why does this work? And now you saw it before your very eyes, right? See how that happens? Okay, now, we can't let all problems be this simple because you'll just say, the answer is 7/2 because I'm smart enough to know that. What can I say? You're right. Okay? But now they can go beyond what you did in pre-calc and take an application like this. And the next one is, I want to find the limit as x approaches infinity of the square root of x squared plus 4x over 4x plus 1. See, now it's not a nice rational expression so you can just look and see. I mean, you can maybe kind of guess. But now I'm going to use that property that we just picked up a few minutes ago, you know, a constant over a power of x is 0. However, what we have to do is multiply it by 1 over the highest power of x, right? What is it? Well, you have to kind of adjust. The highest power I see is x squared, right? But he is under a square root. So technically, 1 over x to the first, right? But now there's a wrinkle. So before we write it down, we have to take a little side trip back into history. I hope they didn't skip this in pre-calc. And that is, what is the square root of x squared? And you say, well, I know what I want to say, but there's probably a catch. You want to just say, well, duh, x?
Is it plus or minus?
No, it's this. That's the correct answer. You check your pre-calc book, it's in there. Okay? And that's what your teacher should have taught you. And you say, well, we never bothered with that because it said assume x is always positive. Well, if x is always positive, then what's the absolute value of x?
Positive.
X itself, remember? So you say, oh, no, not absolute value again. I'm sorry, but that's it, right? Which is equal to, if I kept going, x if x is positive and opposite of x if x is negative. You might recall that. Okay. So, I'm going to have the square root of x squared, right? It's going to be absolute x, but look at here. X is headed for infinity. So what kind of values are these x's? Yeah, when you head towards infinity, x tends to be positive. So under the condition that x is headed for infinity, the square root of x squared is plain x. But if x is headed for minus infinity, then it's opposite of x, and that's going to play a role. Okay, I'm going to multiply by 1 over x, 1 1 over x, okay? The problem is, I can't multiply the numerators because you can't multiply a radical by a non-radical. So you got to change the top to radical form. I'm going to be careful since this is the first time. So I have the square root of x squared plus 4x, and I have 4x plus 1. This is fine, 1 over x. But to multiply this on top, I got to change this to a radical. Now, what is 1 over x as a radical? What's the square root of what gives 1 over x?
Square root of 1 over x.
Isn't the square root of 1 over x squared the same as 1 over x? You say, no, it's absolute value of that. And I say, but if it's positive, the absolute value is just itself. Are you with me? Okay, now we can keep going. This is the limit as x approaches infinity. The bottom is easy. Distribute this and you'll get, what's 4x times 1 over x? 4. What's 1 times 1 over x? Okay? Now that these are both radicals, I can actually multiply them. And if you multiply two radicals, you get a radical back. That's probably true in real life, too. If a radical man marries a radical woman, their children tend to be radicals. You know, it's just sort of a thing of nature. Occasionally it's different, but quite often. Okay, if I multiply this out, what's x squared times 1 over x squared?
What?
And it's under the radical, because you multiply two square roots, you get a square root back. What's 4x times 1 over x squared?
4 over x.
Okay? All right, now we'll do our limit and we'll have the answer. And again, using properties, remember you can put the limit under the radical if you want. And what's the limit of 1? So you have the square root of 1 plus, and then the limit of 4 over x. 0, our new theorem. And what do you get on the bottom? 4 plus 0. And what's the final answer? If you remember that the square root of 1 is 1, right? So what does that mean? It means if I were willing to draw the graph of this particular function, it should have a horizontal asymptote of 1/4 on the right. Okay, now the next problem is, what if I change infinity to minus infinity? How does the problem change? Okay? And we'll see if my lecture on absolute value really made an impression or not. So here's the next one. The limit as x approaches minus infinity. So you can see the contrast. Same problem, x squared plus 4x, all over 4x plus 1. Okay? Okay, before we multiply by something, you have to recall that the square root of x squared is what? Absolute value of x, which is sometimes x and sometimes opposite x. It's this one if what? X is positive. It's this one if x is negative. Okay, where is x headed? So which one of these do I use?
The negative x.
Opposite of x. And so in my first move, because I'm headed for minus infinity, I am not going to multiply by 1 over x. I'm going to multiply by minus 1 over x. Or 1 over minus x if you prefer. Excuse me. You see why I chose that? And I chose it for this reason. I need to change the numerator, just like last time, into the square root of 1 over x squared. Is the square root of 1 over x squared minus 1 over x? In other words, did I do that right? Is minus 1 over x and 1 over x squared square root the same thing? And my other class says, no, 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 you goof. 1 over x squared, when you take the square root, it's 1 over x, not minus 1 over x. I said, well, actually, it's neither. It's absolute value of 1 over x, right? But absolute value of x is minus 1 over x when x is
Less
negative.
than 0.
See? And I know it's negative because I'm headed for, so you got it. Some people just memorize. You're headed for minus infinity, use minus 1 over x. And if you're headed for infinity, use 1 over x. I prefer, though, that it made sense. And that it's logical, because you can only memorize so much, and if it doesn't make sense, you soon get in over your head. But if it makes sense, then you can make progress. So we try to make sure it makes sense. Okay, let's see what's different then. If I multiply out the numerator, you get the square root just like before of 1 plus 4 over x. The denominator, however, becomes minus 4 minus 1 over x, doesn't it? Okay, now do the limit. What's the limit of 1, no matter where x is going? What's the limit of 4 over x? Well, if you're either headed for infinity or minus infinity, it's 0. Denominator? What's the final answer to that? Okay, what's the implication? I have a special kind of problem where the horizontal asymptote on the left and right are two different lines. Didn't happen to you in pre-calc. Well, that's because you didn't have these tools to handle it. So if I would draw a graph of that, what should you see? A nice horizontal asymptote of minus 1/4, y equals minus 1/4 on the left, and y equals 1/4 on the right. And I felt kind of obligated to, I mean, I'm not arrogant enough to think you're going to trust me, but a calculator that costs almost $200, you're going to trust that, of course. They wouldn't dare charge you that kind of money and then tell a lie, would they? I mean, you agree? I mean, this is the sign of the times. We're into technology. Okay, so here we go. Okay, I want to type in the square root of x squared plus 4x divided by the quantity 4x plus 1. And won't you be glad if I finally ever get these calculators? The pretty print says I typed it in correctly, because it comes out exactly like the original problem, right? Is it showing up okay? Let me see if I can do a little better. Maybe better or worse. I feel like an eye doctor. Do you like number 1 or do you like number 2? That's 2. And this is, say 1's a little better. Okay. Unfortunately, I don't have 3 and 4. Okay. Here's the standard window. Zoom 6. Not real clear here. Okay, let's change the window. We'll leave minus 10 to 10, but let's go minus 1 to 1. Well, I thought about that because the asymptotes are y equal 1/4 and minus 1/4, which doesn't take you much off the axes, right? Okay, here we're coming in from the left. And then it quits. And then you get to 0 and it starts, it just kind of zooms up and then goes like that. Okay, let's add a couple. Y equals 1/4 and y equals minus 1/4. Here's y equals 1/4. How does it look? Nice horizontal asymptote on the right. Oh, look at that. On the left, that appears to be it too. I think we did the calculus right. Okay, question for you. Why is there a whole section missing from -4 to 0? No graph. Why is there no graph from -4 to 0? Did you see that square root in the problem? X squared plus 4x. You can only do square roots of what kind of numbers and end up real? Positive. When is x squared plus 4x greater than or equal to 0? Only if you're less than -4 and bigger than 0? Yeah, I'm glad the calculator understands domain. Do you agree with me that 1/4 and -1/4 both serve as horizontal asymptotes? And the calculus found them real easily, provided you remember the definition of the square root of x squared. It's not x, it's absolute x, and sometimes absolute x is x, and sometimes it's minus x. So the square root of 1/x squared is sometimes 1/x, and sometimes it's minus 1/x, depending whether x is positive or negative. How do you know? Check to see where x is headed. Are you good? Okay. Then, your assignment for next time, check the problems in 2.6. There's not a ton of them that were assigned. We'll go over that first thing on Thursday. Then, I also recommend that you check the review that's on Blackboard, and not that you have to work every problem, but look at it, say, if this were on the test, would I be okay? If you say, I'm not sure if I'm going to get that one right, try it. If you run stuck, check the solution that's also on Blackboard. Okay? And if the solutions aren't adequate, bring it up on Thursday and we'll look at them and expand. So, maybe a little heavy, but I think doable. It's part of the night class syndrome, so you can't really, because we only meet twice a week rather than 5 times a week. So you can't break it down into smaller pieces, but are you clear what's scheduled? So work on 2.6. I probably won't give a quiz since there's a test. But 2.6 questions are on the test. And study for the test. And what's going to be your assignment for Monday? Boy, probably nothing, because I don't have time to start continuity and give a test, so I guess that'd be terrible, though. No assignment due for Monday? I'll have to think of something. Okay, that's it. We'll see you on Thursday, ready for a good showing on a test.
Thursday, I guess, go to a little learning lab there.
That's my goal,
What?
barring some traffic accident or something.
Goodbye. See you Thursday.
See ya.